Picture this. A great white shark is cruising through clear blue water somewhere off the South African coast. It is approximately 5 meters long, weighs over 1,000 kilograms, and has been doing more or less the same thing its lineage has been doing for roughly 450 million years, which is to say it has been being terrifying with almost no modifications required. Its teeth regenerate continuously in conveyor belt fashion. When one tooth falls out, another moves forward to replace it, meaning a single shark can cycle through tens of thousands of teeth across its lifetime. Its electroreceptors, called the ampullae of Lorenzini, can detect electrical fields as weak as 5 billionths of a volt, allowing it to sense the heartbeat of a prey animal buried in sand at the bottom of the ocean. It can smell blood in concentrations of 1 part per million across kilometers of open water. Its lateral line system detects pressure changes and vibrations in the water that are invisible to every other sensory system available. It has no natural predators. It is, by any reasonable measure, one of the most comprehensively capable predators that evolution has ever assembled in a single body. And then an orca shows up. The orca does something that seems almost offensive in its specificity. It flips the shark upside down. That is all. It holds the shark inverted in the water, and the shark, which moments ago was the most dangerous thing in this part of the ocean, goes completely still. Not fighting, not thrashing, completely, helplessly motionless. The orca then takes its time accessing the shark's liver, one of the most calorically dense organs available in the ocean, rich in squalene oil, and leaves. The rest of the shark drifts away largely untouched. The great white shark, 450 million years of relentless optimization, was defeated by being turned upside down. The specific vulnerability being exploited here is called tonic immobility, a reflexive paralytic state that sharks enter when inverted, believed to be related to the sensory processing of the vestibular system in conditions of disorientation. It is not a learned response. It is not a situational reaction to the specific orca. It is a hard-coded neurological response built into the shark's biology, and orcas have learned, and culturally transmit to their young, how to exploit it with a precision that speaks to tactical intelligence. The most perfectly designed predator in the ocean has a power-off button, and a marine mammal with a brain significantly larger than the shark's figured it out. Every animal has something like this. A specific vulnerability, a specific weakness built into the architecture of what makes them extraordinary. An Achilles heel that is often the direct shadow side of their greatest strength. And examining those weaknesses, really looking at what specific biological compromises, specific design limitations, and specific exploitable vulnerabilities each animal carries, turns out to be one of the most illuminating ways to understand both the animals themselves and the fundamental nature of how natural selection actually works. Because here's the thing that the great white shark and the orca illustrate so cleanly. Every adaptation costs something. Every specialization that makes an animal extraordinarily good at one thing makes it more vulnerable in some other dimension. The shark's spectacular electroreception, the sensory systems that make it such a formidable hunter, are part of the same sensory architecture that the orca exploits. Natural selection does not produce perfect organisms. It produces organisms that are good enough at staying alive and reproducing in their specific environment, with the specific trade-offs that the available biological toolkit allows. And those trade-offs create weaknesses that are as real and as consequential as the strengths they accompany. Start with the cheetah, because the cheetah's greatest weakness is the direct and unavoidable consequence of its greatest strength, and the relationship between the two is one of the cleanest examples of evolutionary trade-off in any living predator. The cheetah is the fastest land animal on Earth, capable of reaching speeds above 110 kilometers per hour in short sprints, with acceleration that rivals sports cars. This speed is produced by a body plan that prioritizes locomotor performance with extraordinary single-mindedness, a flexible spine that functions as an additional limb in the running stride, semi-retractable claws that grip like running spikes, enlarged nasal passages and lungs for oxygen delivery, and a body mass dramatically lower than you would expect for a predator pursuing the prey sizes that cheetahs target. The problem is that producing this speed requires everything. The cheetah's lightweight, lean frame leaves it with a bite force dramatically lower than other large cats of comparable or smaller body size. A cheetah cannot crush bone. A cheetah cannot hold down large struggling prey the way a lion or leopard does through sustained grip force. And most critically, a cheetah cannot defend its kills. After the enormous energetic expenditure of a high-speed pursuit, which generates so much metabolic heat that the cheetah must rest and cool down before eating, the cheetah is in its most depleted physical state at exactly the moment when other predators and scavengers have strong incentive to approach. Hyenas, lions, leopards, vultures, even jackals in sufficient numbers, all of them can, and regularly do, displace a cheetah from its own kill. Research in some territories suggests cheetahs lose somewhere between 10 and 15% of their kills to other predators, representing a significant caloric tax on an already energetically expensive hunting strategy. There is also a genetic dimension to the cheetah's weakness that compounds the physical ones. Cheetahs went through a severe population bottleneck approximately 10,000 years ago, an event that reduced their genetic diversity to levels so low that skin grafts between unrelated cheetahs show minimal rejection responses, as if all cheetahs are essentially identical twins. This genetic homogeneity means the species has essentially no reserve of adaptive variation to draw on if a new pathogen, a new environmental pressure, or a new ecological challenge appears. The fastest animal on Earth is running out of genetic options. Move to the hippo, because the hippo's weakness is one of those biological realities that seems almost impossible given the animal's physical presence. A hippopotamus is one of the most dangerous large animals in Africa, enormous, capable of moving faster than their bulk suggests, and equipped with canine teeth that can reach 50 centimeters in length. They kill more people annually in Africa than lions do, not through predation, but through territorial aggression and the catastrophic biting force their jaws can deliver. Their weakness is their skin. Hippopotamus skin desiccates extremely rapidly when exposed to dry air. Unlike most large mammals, hippos lack sweat glands and have no effective mechanism for preventing rapid moisture loss from their skin surface when out of water in warm, dry conditions. The natural skin secretion, hipposudoric acid, provides some protection and functions as a sunscreen and antimicrobial agent, but it cannot prevent the desiccation that prolonged sun exposure produces. An animal that could destroy a crocodile in direct confrontation spends the daylight hours submerged not because it prefers aquatic environments philosophically, but because staying out of water during the day would cause measurable, progressive physical harm. The apex of African river danger is, at its foundation, a creature with skin that cannot handle the African afternoon. Crocodilians present a different but equally instructive weakness embedded in what makes them such ancient and effective predators. The saltwater crocodile, the largest living reptile with measured bite forces exceeding 16,000 newtons, is a predator that has survived essentially unchanged for over 200 million years. It has outlasted the dinosaurs, the Ice Age megafauna, and 5 mass extinction events. The design works. The weakness is thermal. Crocodilians are ectothermic. Their body temperature is determined by environmental temperature rather than internal metabolic heat generation. In cold water, or cool air, a crocodile's muscle contractile speed, digestive enzyme activity, immune function, and overall metabolic performance degrades substantially and measurably. A crocodile in water below about 15 degrees Celsius is significantly less reactive, less powerful, and less dangerous than the same individual in warm tropical water. Cold-stunned crocodilians have been documented floating helplessly in cold weather events in Florida, completely unable to thermoregulate their way out of the crisis. The ancient, nearly perfect predator design is fundamentally dependent on environmental temperature in a way that warm-blooded prey animals are not, and this dependence creates specific windows of vulnerability that define the absolute limits of crocodilian range and activity. The elephant's weakness is one that is deeply counterintuitive given the animal's scale. Elephants are the largest land animals on Earth, with a social intelligence and memory documented extensively across decades of field research. They demonstrate empathy, transmit cultural knowledge across generations, recognize themselves in mirrors, and maintain emotional bonds that last decades. And yet the elephant's death, in a significant proportion of cases, is ultimately determined by its teeth. Elephants have 6 sets of molar teeth across a lifetime, emerging sequentially from the back of the jaw and moving forward as earlier sets wear down from the tremendous grinding required to process the huge quantities of coarse vegetation the elephant consumes daily. An adult elephant eats approximately 150 to 300 kilograms of plant material material per day. This is enormously hard on the teeth. When the final sixth set of molars has worn away, the elephant can no longer chew effectively and begins losing condition, regardless of how otherwise healthy it might be. Old elephants in the wild often move toward swamps and riverine vegetation in their final years, selecting softer food that compromised teeth can still process. The countdown to death for an elephant is literally written in its jaw, and nothing about its extraordinary cognitive or social capability changes that particular biological timer. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content, covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. The monarch butterfly's weakness operates at a completely different scale, but is no less consequential. Monarchs perform one of the most extraordinary long-distance migrations of any insect, navigating thousands of kilometers using a sun compass integrated with an internal circadian clock, magnetic field sensitivity, and visual landmarks. A navigational package of remarkable sophistication for an animal with a brain smaller than a grain of rice. The weakness is that the entire eastern North American monarch population converges on an overwintering area in the Oyamel fir forests of central Mexico that covers only a few hectares. The precision of the navigation system that makes the migration possible also creates the catastrophic single point of failure. A disease outbreak, a logging operation, an ice storm at the wrong moment, or a climate-driven shift in the microclimate of those specific mountains can affect the entire migrating population simultaneously because they are all in the same place at the same time. The butterfly's navigational miracle engineered its own vulnerability by being too good at finding one specific location. The blue-ringed octopus deserves examination because its weakness is the shadow side of its most famous attribute. The blue-ringed octopus carries tetrodotoxin, one of the most potent neurotoxins known, with no antidote, in quantities sufficient to kill an adult human many times over. The iridescent blue rings that flash as a warning when the animal is threatened are among the most striking visual signals in the marine world. The weakness is that the warning display is the absolute last line of defense of an animal with almost nothing else available. The blue-ringed octopus is tiny, soft-bodied, and slow relative to most marine predators. It lacks the ink defense that larger octopus species use, lacks the size for physical deterrence, and lacks the camouflage sophistication of its larger relatives. The venom is there because without it, the animal would be essentially defenseless in an environment full of things that would eat it without hesitation. More critically, the tetrodotoxin is not actually produced by the octopus itself. It is synthesized by symbiotic bacteria living in the octopus's tissues. If those bacterial communities were disrupted, the octopus would lose its only meaningful defense essentially overnight. The most toxic animal relative to its size in the ocean is, at some level, dependent on bacteria for its survival. The giraffe's weakness is hydraulic in nature. The giraffe's cardiovascular system must pump blood from the heart to a brain that may be 2 meters or more above it, requiring blood pressure at the heart level that is among the highest of any land mammal, approximately twice human blood pressure. The giraffe has evolved a correspondingly enlarged, powerful heart and specialized pressure-regulating vascular structures at the base of the brain to manage this challenge. The problem emerges when the giraffe lowers its head to drink. The blood pressure that keeps the brain adequately perfused when the head is high in the air would, without compensation, produce dangerous overpressure to the brain when the head is lowered to water level, a change in elevation of potentially 4 to 5 meters. The giraffe's circulatory system manages this through specialized valve mechanisms and vascular networks, but the transition still requires the animal to splay its front legs awkwardly into an extremely wide stance to get its head low enough to reach the water surface. In this position, legs splayed, head down, cardiovascular system managing a significant pressure transition, the giraffe is at its most mechanically vulnerable, least able to stand up and flee rapidly, and most exposed to predators like lions that know exactly when to time an ambush. The most visually distinctive animal on the savanna is most vulnerable during the simple act of having a drink of water. Lions are invincible within their specific ecological niche, which is precisely the framing that reveals their weakness. Lions are highly optimized for stalking, short-distance sprinting, and coalitional prey restraint in open grassland and bush environments with specific prey densities. Their hunt success rate in optimal conditions is typically between 15 and 30%. The majority of lion hunts fail, even under good conditions. In drought conditions, when prey disperses across larger territories and individual hunts become longer and more energetically costly, lion pride dynamics break down as the caloric economics become unsustainable. Large prides fragment. Young males are expelled before they have the experience to survive independently. Cub mortality spikes. Beyond the energetic challenge, lions have a weakness in their social structure itself. Lion prides depend on female coalition stability maintained across years of shared territory and cooperative hunting and cub rearing. When that stability is disrupted by disease, by the takeover of a pride by new males who kill the existing cubs to bring females into estrus, the reproductive and social foundation of the pride can collapse in ways that take years to rebuild. The apex social predator of the African savanna is vulnerable to its own social dynamics in ways that solitary predators are not. The mantis shrimp, whose strike clubs accelerate faster than a bullet and can shatter aquarium glass, has a weakness built directly into the maintenance of its primary weapon. The clubs must be periodically shed and regrown through molting. And during the molting period, when the old clubs are gone and the new ones are still mineralizing and hardening, the mantis shrimp has no effective offensive or defensive capability. It cannot strike. It cannot defend its burrow. It retreats into hiding and waits in a state of temporary physical vulnerability that is as complete as the invincibility of its fully armed state is impressive. The most powerful punch in the crustacean world is offline for weeks at regular intervals throughout the animal's life. The mantis shrimp's vision is equally extreme and equally double-edged. 16 types of photoreceptors compared to the human 3, processing color information at a level of complexity that human visual neuroscience cannot fully model. The weakness is that this extraordinary visual apparatus is specialized for rapid color processing rather than color discrimination. Mantis shrimp are actually worse at distinguishing between similar colors than humans are, despite having many more photoreceptor types. The 16-channel color vision system processes color information in a fundamentally different way from the comparison-based color processing of human vision, optimizing for speed of decision-making rather than subtle color discrimination. The most sophisticated visual system in the animal kingdom cannot tell the difference between certain shades that a human child could distinguish easily. The albatross carries one of the most poignant weaknesses in the bird world, emerging directly from the mechanics that make its oceanic life possible. Albatrosses use dynamic soaring, a flight technique that extracts energy from the wind gradient over the ocean surface, allowing them to travel thousands of kilometers with almost no muscular energy expenditure once they have reached sufficient speed in sufficient wind. This is how albatrosses circumnavigate the Southern Ocean, spending years at sea without landing. The weakness is simple and absolute. No wind, no flight efficiency. In calm conditions, when the ocean surface is flat and windless, albatrosses cannot use dynamic soaring and must resort to flapping flight, for which their long, narrow wings, optimized for soaring, are poorly suited. The energetic cost of flapping flight in an albatross is dramatically higher than the soaring flight their wing structure was designed for, and being caught in a large calm area can create an energy emergency. The bird that can circle the globe spending almost no energy on flight is helpless without the specific environmental condition, moving air over a surface that its entire flight strategy depends on. The thread connecting all of these weaknesses is the same thread that runs through every biological trade-off across the entire evolutionary history of life on Earth. The resources available to any organism are finite, and every allocation toward one capability is necessarily an allocation away from something else. The cheetah spent everything on speed and had nothing remaining for fighting capability or genetic diversity. The elephant invested in cognitive sophistication and social complexity, and is ultimately killed by its dental schedule. The great white shark built the most comprehensive sensory package in the ocean on a vestibular system that an orca learned to exploit 450 million years later. This is not a failure of natural selection. It is exactly how natural selection works. It optimizes within constraints, makes trade-offs, and builds toward the specific demands of a specific environment at a specific specific historical moment. When the environment changes, when a new competitor appears, when conditions shift in ways the optimized design did not anticipate, the weaknesses that were invisible in the original environment suddenly become the most important thing about the animal. The orca did not defeat the great white shark by being more impressive overall. It defeated the great white shark by finding and reliably exploiting the specific vulnerability that the shark's extraordinary sensory design had inadvertently created. That is not brute force. That is intelligence applied to biological weakness. And it is a reminder that knowing exactly where something is vulnerable is sometimes more powerful than being stronger than it in every other way.